All right. Hi, everyone. Welcome to Astronomy on Tap for one of another events here in London or wherever you are, actually, because this is virtual and online. So today we're going to talk about one of the most important discoveries in cosmology, discovered by mistake and studied for decades. This is the cosmic microwave background. And to discuss this, we have with us Pablo Lemos from UCL, and Chiara will introduce him as usual.
Hi, everyone. Yeah, welcome to this session of Astronomy on Tap. As Roman said, our speaker today is Dr. Pablo Lemos. He's a researcher at UCL, and today he'll talk about his research focused on cosmology and the cosmic microwave background. So I was talking with Pablo earlier, and we agreed on the fact that to pursue a career in research, like passion and curiosity are surely fundamental, but as fundamental is having a person close to us who can encourage us to, follow our passion and what we like. So regarding this aspect, Pablo, you wanted to share a special memory with us?
Yes, I do actually. Thanks. Hi, everyone, first, and thanks for the invite and for the great work you guys have been doing with this. It's actually been really good to follow the talks. And yeah, big thanks also to all of the family and friends that have actually listened to my invitation, because I think nothing shows love for a friend or family member like taking half an hour out of your day to listen to me talk about astronomy. And yeah, like Chiara said, I was asked about my sort of what led me to astronomy, and I don't have a particularly inspiring or I don't know, motivating story, but I wanted to share. So I'm going to put already my screen on. Oh, that's very pixelized. It's a photo of my dad who passed a few months ago, and he always taught me to find something that you like and really pursue it, and really try to, I don't know, give it all and I don't know, follow your passion, not follow money, not follow anything else, follow something that you're passionate about. And I think that is what actually led me to a career in astronomy that otherwise I wouldn't have probably. And of course, I know that he would be listening to this if he was around, and I wanted to thank him for everything he did for me. And on a more positive note, I also wanted to share something personal, which is that as of 11 days ago, I got engaged to this beautiful lady right here, who's probably listening to the talk in our living room right now and hating that I'm putting this photo up because she didn't know that I was going to do that. So on that note, I think that's all my personal stuff, and I'll start the talk if that's okay.
Sorry, just a sec, Pablo.
Yeah.
Yeah, stop sharing the screen. Thank you very much for sharing this. It's really nice and touching. Okay, I think so what we do during the week is we share questions on social media, and so then people can follow your talk and try to answer live when you give the answer. So I think Corentin has questions, and we'll just recap the questions so for people who were not on social media.
Yes. So we had this week we had 3 different questions and a couple of puns as well. So as you can see, why is the word microwave in cosmic microwave background? So one of the wrong answer is just here. It's because it's a microwave as background with a cosmic stuff in it. So that's the first question. Why do you think there's a microwave in cosmic microwave background? The second question is, why are telescopes to measure the CMB? So CMB is cosmic microwave background, such as COBE, WMAP, or Planck. Why are they sent to space? And the third question is, what were the people in Bell Labs looking in the 60s when they accidentally detected the CMB? So you can post your best answers on the chat. I think it's in this direction, or on Twitter if you use Twitter, and follow Pablo's talk to probably get some of the answers, and we'll answer all of them at the end of the talk. It's your turn now, Pablo.
All right. I think you have to stop sharing first. Yeah. Let's see. Okay. All All right. Also, I forgot before, this is Astronomy on Tap, so I decided to bring a beer with me. So cheers to everyone who's listening, and I hope you're doing the same. All right. So yeah, like Corentin mentioned, I'm going to talk about the story of the cosmic microwave background. I'll call it CMB in short as well, just because it's a lot to say. And I want to talk not only about why it's important to astronomy, which is a lot, but also I want to focus a lot on the human side of it. There's like some really interesting human stories behind the discovery of the CMB, and I think it's something that is perhaps not widely known, and it shows a bit of how science actually works in the making. So to talk about this, I'm going to kind of do a small trip back in time, and I'm going to go back to 1940 and talk about a bit what we knew about cosmology back in the day. So first of all, we had just discovered the size of the universe, by which I mean we had very recently found out that a lot of the bright dots that we saw in the sky were not stars, they were galaxies, each with millions of stars, which had made us look and feel a lot smaller in the universe than we actually thought we were before. And so this was one of the big discoveries that had happened recently. We had a new theory of gravity, and you might have heard of the man who came up with that. And the third one, and perhaps the one I want to focus on the most, is that we had just discovered the universe is expanding, right? So things are moving away from each other. Now, there's several people to credit for this, but I think one particularly interesting one is this woman, Henrietta Leavitt, who worked as a computer in Harvard, because that was a job that women used to do a lot at the time. So there were no actual computers, so she literally had to do the job of a computer. And while doing that, she discovered an important property of certain objects that allowed us to discover that the universe is expanding through people after her. So this discovery of the expanding universe led these two people to come up with two theories of what the universe actually is and what the story of the universe actually is. One of them is George Gamow, and the other one is Sir Fred Hoyle. And as I said, they had two competing theories. So George Gamow said, if the universe is expanding, as we look back in time, things are closer and closer to each other. And we get to a point where things are really, really close. The universe is really hot and dense. And so all the elements would have formed during this very hot soup of universe. And then as it expands, it cools down, and that forms the galaxies and so on. So his main idea was a universe with a history. It used to look different than it is now. The other camp was Fred Hoyle, who didn't like this. He thought the universe had to be eternal, and so he thought if the universe is expanding, it's probably forming new matter as it expands, so it's always actually looked the same. So it was a pretty friendly rivalry, but it was a rivalry after all. They really disagreed very strongly on this. They each had like a kind of a camp of followers, to the extent that actually the name Big Bang was actually coined by Hoyle to make fun of Gamow's theory, because he thought it was ridiculous that there would be some kind of very hot universe. So these two theories kind of competed for sort of 20 years with no resolution, and the resolution came in the 60s with echo balloon satellites. Now, when I first heard about this, I think the person who was telling me was surprised that I had never heard of them, but I think perhaps the younger people in the audience will agree with me that this is not something that we know about. So the idea with these is, I think there was an animation, there we go. It's literally a huge balloon, a huge metal balloon that was sent to space. So this is an animation of one of them actually being blown up in space. And the idea was to send electromagnetic waves to them and bounce them back, and they would act as satellites, like the ones that we now have for our television and our phones and so on. So they were sort of the first satellites. It was the US's attempt to try to kind of get ahead of the Soviets in the space race. And in fact, I have a cute animation of a television broadcast explaining how this works.
About 50 of them, orbiting at a height of about 3,000 miles. As the one you were using moves out of range, you would switch to the next one coming along, and so on. And if you wanted to send, say, a telephone message or a television program to some area not covered by any single satellite, the signals might be bounced from transmitter to satellite, back to Earth, up to a second satellite, and down to the destination. That way, you could maintain continuous transmission of telephone calls and television programs to various parts of the Earth.
Right. So with that idea, we go back to something called Bell Labs in the US, and these two people called Penzias and Wilson, who were working for Bell Labs, and they were trying to do the work of detecting the signals bounced off these echo satellites. So to do that, what you have to do is make sure there is no contaminant, right? Because, for example, the atmosphere is a contaminant in the signals. There can be perhaps interfering signals around. So a lot of their job was to make sure that there was no contaminants around so that they could detect this cleanly. And what they kept finding was that there was this kind of background noise that was everywhere. It was coming from all directions. It was not coming from a specific point in the sky. And it didn't seem to go away no matter what they did. They tried to play with the instrument. They tried to look at different areas, and it was just constantly there. It was not moving. They even got to a point where they thought they had solved the problem because they found a large amount of pigeon feces in their antenna, and they went to clean it, hoping that would fix the problem. I actually have a little pigeon there. But turns out that the noise was still there. And it was not until one of them went to talk, in fact, Penzias went to talk to some of the people who had been following up on George Gamo's theory, and they were told that if George Gamo's theory was true, there would be like an afterglow from this Big Bang explosion, and that perhaps that's what they were detecting. And in fact, this work earned them both Nobel Prizes after that. So what were they seeing? What is it that they saw in this work? Basically that. It looked the same exactly everywhere. It had a temperature of about 2.73 Kelvin. It was completely boring and isotropic, but it had the role of confirming the Big Bang theory and ruling out the steady state theory of Fred Hoyle. So all of a sudden, this discovery took us from not really knowing how the expansion of the universe works, and whether it's constant or if it has a history, to confirming one of these theories. It was already massive, but people wanted to go further. So there was a prediction that in the Big Bang theory, this uniform radiation would actually look different at different points. There would be very, very tiny differences between one point and another, and those differences would kind of be the seeds to all the structure in the universe we see today. They would be the seeds to the formation of galaxies and so on. And so people from this point onwards spent a lot of time and effort trying to detect these seeds. And so finally in 1992, the COBE satellite managed to go from this to this. And these are, again, the seeds to the formation of the universe. And to get an idea of how small these different points are, if this point has that temperature, a hotter point had that temperature. So look at how tiny, tiny, tiny these differences are. So it was really a work of amazing precision and engineering to manage to detect this with such accuracy, with light that was emitted soon after the Big Bang and has been traveling to us all the way since. We managed to detect these very, very small differences. And in the words of George Smoot, he said it was looking at the face of God. And you can really understand, we were looking at a baby universe. It is truly one of the biggest feats of humanity in the history of science, I would say. So from 1992, I want to jump to today. And what do we know today? Well, we've gone from like that rough picture that I showed you earlier to a much more precise picture of what the universe looks like. So now we know that the universe starts with something that we call inflation, where it expands really quickly. Then it emits this cosmic microwave radiation. It goes to something called the dark ages. It forms the galaxies, and now it's accelerating. How do we know all of this? Do we know this in so much detail? We even know the numbers. We know the times. How do we find out about this? Well, a lot of that comes from the CMB as well. And the best measurement of the CMB, and one that has perhaps really helped paint this picture, comes from a satellite called Planck. So I have a small animation about Planck. This is from the European Space Agency, which was in charge of Planck. So it operated between 2009 and 2013, but its science results were not finished until 2018. And as you can see, it measures the sky all over the sky. So it does it from space so that it can actually get a measure of the whole sky. And it gets a map kind of like that one in the picture, which is far more precise than COBE. So just so you get an idea, this was COBE. This was something that came later called WMAP, which is far more precise. And then this is Planck 2018, which is, as you can see, the level of detail here is quite impressive. And now, so the next thing is, now we have this map, this very detailed map of this cosmic microwave background, but how do we know from this to that image of how the universe works? What are the mechanisms? What are the numbers? So the idea is the following. We have this map. We do some kind of data reduction, and from that we get this, which is called a power spectrum. It's basically reducing the map to something simpler. Now we get our model of the universe, where we have maybe some amount of dark matter, dark energy, and so on. We put it through a scientist with a computer or a cute animal. And then the scientist will tell us, for that universe, this is what that curve should look like. And now what we're going to do is we're going to compare the two, and we're going to try to find a universe that has the curve that looks the most like the one, like the real thing, like the one that we see in the data. Incidentally, that was actually what I did in my PhD. So we can find things like, for example, how much dark energy there is in the universe, which will change the shape of this curve, kind of like that. We can ask ourselves how much dark matter there is in the universe, which will change the curve, but in a completely different way. We can ask how quickly the universe is expanding, and so on. And there's actually 27 of these numbers that we can change. So it's a complicated task, but eventually we find this, which is called the Planck cosmology. The model we call lambda CDM, mainly because it's formed of dark energy and dark matter. And as you can see, the kind of agreement with the observed thing is actually astonishingly good. And so we're very confident that the universe seems to behave like this. And what does this actually mean for the composition of the universe? Well, we have roughly 68% dark energy, 27 dark matter, and 5 visible matter. Now, dark energy and dark matter remain elusive. We don't really know what they are. We know how they behave, and we know that if they behave the way we think they behave, we get that curve agreeing that well with the points that we see in the map. But we don't really know what they really are. We don't really know what they're made of. So challenges do remain to cosmologists despite all of this amazing evolution in the last few years. So yeah, to conclude, so the CMB has taken us in the last sort of less than a century from really knowing very little about the universe to knowing things to incredible accuracy. We know the components, we know the history, we know a lot, and a lot of that is thanks to the cosmic microwave background, amongst other observations. But there's still a lot for us cosmologists to do. We still don't actually know what these components are. So there's actually a lot of work and a lot of exciting times ahead and a lot of exciting discoveries. And I would like to finish up on a note that you probably have noticed that all the scientists I showed today are white and mainly male. This is a problem still today in academia and in astronomy in particular, and something that we have to work hard to change to make sure that the next pages in history of science are a lot more diverse and a lot more mixed. So yeah, thank you very much. That's my talk. Do I still share?
Thank you very much, Pablo. That's a great talk. So yeah, so if you're watching us, please start asking questions. So I know we're having a 20-30 second delay. So in the meantime, so while you ask question on YouTube, then we'll ask Pablo directly. Let's go over maybe quickly the answers to the questions. Corentin, maybe, or we can.
Do you want me to stop sharing?
Yeah, perhaps, yes. Right, okay, cool. Maybe just Corentin, if you read questions.
Yep. Ooh. Is it working? Yep. So maybe I can just read the questions and then Pablo, you give the answer. So the reason why there's microwave in cosmic microwave background, why is that?
Yeah, I didn't really respond to that. So when light is emitted in the cosmic microwave background, it's actually mainly visible light and ultraviolet light. But I don't know if you are familiar with the spectrum of light, where microwave is less energetic than visible. So as the light travels between the Big Bang and us, it's losing energy. So it's going slowly from visible to big microwave when it arrives to us. So it has nothing to do with an item you use to reheat your food. It's just the type of light that we can observe and that the people in the labs observed in the 60s.
Okay, and so why are telescopes to measure the CMB sent to space?
There are several reasons, but I think one of them that I kind of showed in the talk in that little animation is that you want to get an image of the whole sky. So if you can imagine that if your telescope is somewhere, I imagine in the UK, other than the problem with the clouds, you would only be able to see the things that you can see from the UK, right, which would be the northern hemisphere of the sky. But if you go to space, you can actually see the whole thing. Another problem is the atmosphere for the type of light, the microwave type of light, and especially infrared. There are problems observing it through the atmosphere. So if we get out into space, we can see without those issues. And the third one, I think I responded.
Yeah, I think you did. Yeah. So they were looking for pigeons.
All right. Let's move on to questions. Oh, wait. Where are you? Yeah, here you are. Yeah, so lots of people thanking you, Pablo. So, you can please like and share the video. Meanwhile, we have a first question, maybe, Chiara?
Yes, we have a question from Arthur. What's the next step for future CMB studies?
Yeah, so there are now, so it is now kind of accepted that measuring the temperature of the CMB has been done almost as well as it can be done. This is the feat of Planck and the amazing achievement of Planck. Now people are trying to measure something called the polarization of the CMB, which is a different property of the light that Planck measured, but not to as high accuracy as the temperature. So now there is a big effort to try to measure that to high precision. So there are especially something called Simon's Observatory in the US is trying to detect that with high accuracy, and we'll see what discoveries they find with that.
So there is another very important question. Someone is asking, what are you drinking? We're not endorsing anything, we're not paid by any brand.
We're not. I wanted to drink a beer called Estrella Galicia because that's where I'm from, but I couldn't find it in any store today. I walked around and so I'm drinking a Portuguese beer called Superboc that is nearly as good. Highly recommended.
Right. Yeah, we should do a post. Yeah, we should do that actually. We should ask every speaker for the beer recommendations. That would be quite fun.
You could get the money on the side as well.
So yeah, anything else you want to share maybe on the what you learned during your PhD? So how to be the cute animal scientist between the model data?
Well, I think for the people, especially the younger people in the audience, who are thinking about doing a PhD, it's something that really takes you from a rough, like the kind of understanding of your subject that you get in a master's to sort of from the understanding of the theory and the things you learn in textbooks to actually understanding how things are done, right? Which is so much, I don't know, so much less pure than the things that you learn in textbooks, and there's so much more trial and error and so on. But it's truly amazing to see it happen and seeing it in action, especially when it's something that you actually are interested in. So for me, that and the fact of working, and I was lucky to work with the Planck collaboration, which had some amazing scientists that I learned a lot from. In particular, I guess I would thank my PhD supervisor, George Sathiou, who was extremely useful and really pushed me to learn a lot of stuff.
So for those who don't know, George Sathiou is probably the lead of Planck science, right? And then, I don't know, the great god of CMB, perhaps.
I know that he's not seeing this talk because otherwise you would have 10 comments of things that I've said wrong. So.
Right. We have another question.
Yes, from Mauro. How much do you think it will take us to know in better detail what dark matter is?
It's a very good question. I think it's something that could take a very long time, or it could take a very small amount of time. So now almost every year we have some new form of telescope or some new observation that is coming, that is trying to understand dark energy and dark matter. And we're always hoping that that is the one that will change things. But I think if you had asked someone 20 years ago, they would have said the same thing, that maybe we were about to find out and we haven't yet. So I think it's really hard to predict. I hope that will be soon enough and that we'll all be able to see it in our lifetimes, but it's really hard to predict.
So we have another question on the observational side. Has the temperature measurement changed much from WMAP to Planck?
Yeah, well, I don't want to reshare the screen. Basically, should I share the screen to?
Yeah.
So. So you can kind of see it in this animation where the main difference is that Planck kind of has higher resolution, right? It kind of goes into finer detail. And that actually translates in this plot in going further into the right. So the more to the right, the more to the smaller details you're going into this curve. So what Planck learned is basically WMAP finished somewhere around here, and Planck managed to take us a bit further into smaller and smaller kind of scales, smaller details. So obviously the smaller points mean that we can understand things that happen in a smaller range. So that's where Planck took us. But now it seems really hard that we've actually in temperature managed to go any smaller than that, at least not significantly.
But no change in the mean temperature, for example.
Oh no, the mean temperature since COBE has been basically the same. The differences are so small that the mean temperature hasn't really changed.
Which is really cool because it's 3 different space missions.
Yeah.
Developed, again from scratch, never tested. I mean, it's a bit crazy.
It is actually,
yeah. Great. I think we have another question.
Yes, we have an interesting question to ask to a cosmologist, I think, who is working at the edges of the universe. So the question is, could you tell us what your favorite planet is and why?
Oof. Is it boring if I say Earth? I don't really know. What would be my favorite planet? I guess Mars, because I'm hoping that in our lifetime we will manage to actually send humans there, which I think would be amazing, and it would be kind of the same that it was to our parents to see the moon landing. But I have to say, as a cosmologist, and like Chiara is slowly referencing, I don't really know that much about planets. So if you take me out of the solar system, I don't actually know that many.
So we had 2 talks. The 2 previous talks were on exoplanets. If you want to watch, yeah. But it's true that you're now looking at 4 people that don't touch exoplanets. That's so it's the worst crowd to ask. Okay, I think we're done. Thank you very much. Lots of questions.
Thank you guys, and thanks to everyone who attended for the really amazing questions.
Yes, thank you again, Pablo. Thank you, Chiara, Corentin. Before we leave, I just want to sneak peek at next week. So next week will be our last of the AoT Online before we take a break for mid-July, mid-August. And we'll have a guest speaker from Durham. So it's not exactly London, but location, space, and time doesn't matter anymore. So we'll talk about the tale of merging galaxies, and you can see in the background 2 cute galaxies merging. So that's next week. If you subscribe to the channel, you will already get the link for next week. I think it's one of the planned events. And I can stop sharing. Yes. And you can already share this. Don't forget to share and like, and you can subscribe to the channel, of course, if you want to see more videos. We have now 10 or 12 videos on a lot of different subjects if you want to go forward. And also, if you go to our YouTube webpage, we have links on the homepage to other AoT in the world. So more astronomy than you could possibly ever watch, I think, because everyone's doing AoT online now. So you have longer formats. I think we're more bite-sized formats. And yeah, hopefully at some point in the future, we'll be able to meet all again in a pub and give you prizes and actually taste the different beers together. Thank you. Thank you again, Pablo. And
thank you guys.
Next week.
Thank you, Pablo.
Thanks.
And I will stop the stream. Yes. Okay.